All right, welcome. This will be the final problem we're addressing. This is one of many parts, so this is just part one. And we're going to run through it really quickly. Part one is essentially proving that this function is a solution amongst this equation. So this first part is the derivative of temperature with respect to time. And over here we have the heat diffusivity. I hope I'm saying that right. It's really hard for me to say. And then we have the second derivative of temperature with respect to position. So let's look at what we have first off. We have time, we have position, so we're already looking good. It's related to temperature. We have alpha, heat diffusivity. I'd say we're looking good. Now, the conditions of the problem were, as of right now, not really necessary, but heat diffusivity is 1 meter squared per second. Length of the bar that we're talking about here, so if you have this bar, you can influence the heat of this bar as being the same throughout, as long as it's not affected by an outside object, let's say, that's supplying this heat. And each section is going to be by 1 meter, so we'll have 50 sections. So we want to prove that this is a solution in this equation, 100% doable. In fact, let's start out in general. So if we were to plug in this on this side, we're just taking the derivative of t. Only this part has t, so let's run this through. So on the left side, when you're taking that derivative of t, only this part is brought down out here. This part has no part of t, so this is basically treated, I don't want to say as a constant, but it's basically just left entirely alone. So now let's look at the other side. The other side clearly has an alpha that we can pull out immediately. So we can just leave that there. We're taking this second derivative with respect to x. So contrary to what we did on this side, we're leaving this part alone this time, and we're focusing on this part. However, you might have noticed by now that this I is an imaginary number, and I is represented as... If I is represented as this, we'd have a problem. But let's just see how this works out before we say that we can't solve this. Okay, a little slanted there, but as you can see now, the problem we had before, this I, is now I squared. And I have great news for you, because if you square this value, it just becomes -1. So now the imaginary number is no longer a problem. So let's rewrite this second half and see what we get. So I moved the k squared over to try and demonstrate this better. We have negative alpha k squared e to the power of negative alpha k squared t times e to the power of ikx. These are equivalent. Therefore, this is a solution of this equation. Everything checks out, perfectly flows through. You have your answer to part one. All right, so as I mentioned previously, part one is done. Now we're moving on to part two, where we're going to come up with an equation to help us work around this thermal diffusivity equation. So alpha right up front, we've seen this before. I'm just going to clarify something that we're essentially taking the derivative of a derivative. Having that been said, let's go ahead and look at this side of the equation. So the change in temperature with respect to time. So how do we think about this? Well, actually, it's pretty simple. Let's just think of it as this. So the superscript we have, this exponent, this n plus 1, this is representative to the change in time kind of idea, whereas j is more towards the change in position. However, this side is with respect to time, hence we're over delta t here. What about the other side? The other side is much more complex, as you'll see here in just a moment. Almost forgot alpha. So now we have this. Remember how I said that this is a derivative of a derivative? That's just why we have this extra delta x down here. And then we have essentially two derivatives, right? Because one has to be smashed up there. So we have the position, let's say before, so to the left of the, let's say our observed position. And we're noticing that change. So let me write this out. Maybe it would be better to visualize. So I put kind of like a bullseye mark right here, as hopefully you can see. I'm standing on the wrong side of the board, but let's say that this is our observed value. So this is Tnj. So that's what that number, or that, you know what I mean? It represents that. If we want to look towards the change to it, this one is Tnj plus 1. And if you want to go over here, that's Tnj minus 1. So observed to the left, observed to the right, the observed or the middle. Now that's how that is explained. So let's go ahead and essentially just clean this up, and I'll explain it when I'm done. So we've cleaned this up. So we have the Tn plus 1j is equal to our Tnj, which is remember, the middle point, plus r, which r, as you can see, I've rewritten over here. R is just a manipulation of the values that we for certain know. So alpha, thermal diffusivity, change in time over the change in position squared. And then you'll see we basically have this kind of like an ABC kind of thing. A, or 1 minus 2 plus 1. I'm not sure if you're catching on to that. I don't exactly know the words or remember the terms. But when we simplify it, you get the before minus 2 times of the middle plus the end, or the after. So this equation is what we're going to use in code to help visualize and compute that change in temperature through this entire length of our bar. So I will see you in the coding section, or part 3, in just a minute. Okay, time to begin part 3. Part 3, we're going to be essentially coding this entire problem out and eventually come back to it and go back to the whiteboard. So from previously on the whiteboard, we had this bar, right? I'm trying to look at the camera. We had a bar. And from beginning to end, there's basically a constant heat throughout this bar. And we can reflect this, or try to show this visually through arrays and plotting. So as you can see here, I've already put in some imports. Obviously our friend numpy and plots, basically. Numpy and plotly to help solve these things. And then you'll see from Skippy in a while, that's not too important here in the beginning. So we're going to start off with simple things. So our change in position, or essentially our segments, we'll start off with, let's say 20 for now. Oops. There we go, 20 for now. And then time intervals, and let's just put that as 20 for now as well. If you recall from our equation, our specific R value, we will write that out. So R is equal to alpha times the delta T divided by delta X, and that's V squared. So obviously we need to define these. So the alpha in the problem is just 1, and then delta X. I know the entire length was 50, however, we'll just keep that 1 as well. And then delta T, let's put it at half a second for now. So now these values will help us calculate for our R value, which, like I said before, was in the equation. We haven't put that in here yet, but R will be needed for that equation, so it's good to have done that in advance. So let's move on to that array to help you visualize that I mentioned. So the array will be for position. We can use numpy to help us here. I'm actually getting ahead of myself. This is not the right array I want to use. Let's finish it so we don't get a fragment. We actually want the arrays T, np dot full array, size of nx, so shape of nx, and then we'll put it as 20. So I need to connect those, sorry. Didn't work. I thought I just... Am I stupid? Whatever. So what we've just done here, I could really care less about this now. What we've just done here is T equals n numpy full. We've basically made the same length of our nx. So our nx is 20, right? And I set the values as 20.0, so as a decimal point. So we have 20 20s in an array. And that will represent, it's our delta x, remember, it's our number of segments. So we have 20 segments, all at temperature of 20, we'll say Celsius, obviously, because Fahrenheit is inferior. And we will go through and we will essentially change certain parts, and we're going to see this heat diffusion go in. So I'll go back up here and I'll finish this. This will be multiplied by delta x. And the reason that this part is multiplied by delta x is to, how do I explain this? It's to set up the change, like our position. So we have 20 segments, right? And we want to find basically the position at each part of the segment, as in their distance away from the initial starting point. So essentially, each segment's the same, so 1 and then times 2 times 3, so we're getting the distance instead of the same number over and over again. So, as we mentioned before, we are changing the ends of the bar to varying degrees. So the left end at index 0 will be 50 if you're imagining the array, and then the indexing from the right with the index of -1, that's where the negative comes from, we set to 80. So let's try and show this. While I'm setting this up, I apologize again. I'm not the most wonderful of typers in the world, and I'm certain, but I'd like to think I'm not the worst. So there might be errors or misconceptions while I'm doing this. But I promise you I'm not doing it on purpose. Let's name this test or something. Oh, it's awkward. Let's try that again. Aha, like I said, I promise I wasn't doing it on purpose. So, seeing as how I had a problem trying to show you the array earlier, this is what we're looking at. So we had originally an array down here, you can see my cursor, of just 20 20s. It was a terrible year. Anyway, we changed the initial indexing to a 50. All the internals were kept at 20s. And then the final, that's right. There we go, much better. So initial, 0 is 50, 20 is 80, and all the internals are 20s down here. I'll be going too fast, but you can see the line. So far so good. We've ironed out the first part of this. But you might be asking, Michael, where's the equation we solved? Where is it? Show it to me. I'd say hold your horses. We're about to do that next. So first things first, we have to run this past you again. The equation of t is represented, I don't want to say strangely, but it's going to take array manipulation. So I'm going to write it out first, and then I'll explain it to you. So here's where it starts to look strange. Like I said, though, I will explain it to you after I write out the entirety of it. Here's where R comes in, finally. Yeah, so that one's right. And then minus 2 times t of 1 to -1, then let's add t just the -2. That looks correct to me. So let's explain this again. T from 1 to -1 is encompassing essentially the entire bar, with the exception of the initial indexing. Same thing goes for then T on the other side, right? I mean, come on. Plus R, and we all remember what R is. That's our thermal diffusive. I can't say that word, but I hope you understand what I mean when I say alpha. Times the delta T over the delta X squared. That's R. And then we have T, and then you have this weird array command. Some of you may know it, some of you may not, but this whole idea is if you're looking at that bar and you see like a grouping of three slots anywhere in the bar, this first grouping, T bracket 2 colon N bracket, is shifting it to the right. So we're getting right of where, let's say, we're observing. Then this -2 times T of 1 colon -1, that's the center. And then you may have thought by now, colon -2 is then shifted to the left. So it's kind of giving you this perspective of that, kind of like the J positioning. That's what this J is doing. We had J plus 1, J, and J minus 1. That is what this array is kind of helping us display. And you will see shortly when we plot it. So let's just plot it and see what happens from there. That's not supposed to happen. How did I forget to... That's supposed to happen. So, you can see a little... Oh, no you can't. There you go, now you can. So, we have test, right? Probably could have named these better. You have test, you have this original, you can kind of see it here on the edges, and over here as well. This is our original bar heat on both sides, right? So 50 is abstain, that's why in the initial part you didn't see an indexing value of 0. That's why, and as well as technically you never saw an indexing value for the final part, because it doesn't actually include -1. Although you saw -1, it never actually includes on that right side. That's the cutoff. That's not included. So you see this like inner parts, right? All this just mesh. But you also notice this kind of, where's a good place to look? Look at this purple to orange. It's kind of jigging value. Let's see, what would be a good way to demonstrate? How about here? I don't know about you, but that doesn't look like what we just looked at. And we're hitting temperatures around 400. I don't know about you guys, but that doesn't seem very balanced or normal to me, so. I'd say we have a problem. Now, I want to say one thing. The problem is not the code. This code, albeit some of the numbers temporarily are subject to change, obviously, based on the conditions of the problem. This is just for demonstration. The code is fine. Everything code-wise that we have done is fine. And I'll demonstrate this slowly. So 0.5 was fine, 0.6 wasn't. What about 0.55? I don't know about you guys, but we got a problem. So 5.5 wasn't good. So I'd say that's better, right? I'd say that's reasonable. But you can see when you change that delta t value, we're having major problems that really shouldn't be there. You should still get this kind of smooth look, right? But as you saw, and I'll go back here for a second, that this obviously needs a fix. It's very unstable. And we're going to fix this essentially in part 4. And I will see you back there in just a second. Okay, so from the previous coding session, we've noticed that our R value is rather unstable. So we need to find out why and how to fix it. So to begin with, let's reimagine our bar here. So we have a bar index of 0 to 7, and let's represent each one of these as delta x. So for the first part, we have a bar that over time, each increment measurement is changing its temperature. The heat is diffusing within the bar. And the best way we can to visualize this is we're going to make a summation of this part. So let me write this out. So the summation of all of the k values, because k we were just ignoring as a number for right now, and we're still going to keep it that way, but we have this constant value that if we were going to use differential equations, we could solve for, but take around 10 to 20 minutes probably. So we have this summation. Now this summation has some get-arounds that we can use, but for right now, we're going to focus on a specific k value. We don't care about all the k values, and that's why this bar comes in handy. So here is what we're going to do. We're going to rewrite t and x. So for x, we can write it as such. A equals j delta x. J just represents a number 0, 1, 2, 3, etc., all the way to 7 on this bar. And it's just giving us that distance that we're going to sub in down here. Whereas t is much more the same. T equals n delta t. And that basically just says to us that we're not going to focus on every little second of time, but we're going to focus on specific sets of time based on our set increment. So n is like j of 0, 1 through however many iterations we're going through. So we would substitute that in right here. And we're going to kind of jump a step real quick. So I'm going to show you that here. So we iterated t here, or kind of defined it. So we have, contrary to the previous equation that we've written, was t to the power of n plus 1 and then sub j. So this one is just tn sub j, because we are defining a specific n and a specific j that would allow us to use this more precisely rather than looking at the sides. Now where do we go? It's a good question. So we want to bring up our previous equation. So let me refresh your memory. Here's our problem child r. This was the previous equation, as you can see, the tn plus 1j. Now, where is the significance here? So let's talk about the difference first. The only difference between these two on base level, not including these parts here, is this n plus 1. So if we were to account for this n plus 1 here, here's what we would get. If you have taken differential equations, you'll come to understand this part, as I kind of was thrown through a loop there for a second, that if you have a n plus 1, kind of like a chain, so let's go through and say like n plus 1 and n minus 1, whatever, and then you just had n to n minus 1 to whatever, a lot of it cancels out, but since we moved it and shifted it, we are left with Tn plus 1 of j is equal to Tnj e to the power of alpha k squared delta t. The n isn't of significance as of anymore. So as you can see here, this can be set equal to the second part. So which means we can rearrange that second part to more readily accommodate. And as well as, before we do that, before we set them equal to, I want to talk about this part. So if n plus 1 to n can be related with such a change for the t value, surely j can be related to the x value, and that is 100% correct. So I'm going to do a big chunk here and rewrite this. So we just brought down this, the substitute for the Tn plus j is equal to then, we just brought down plus, and we pulled out this Tnj from up here, essentially, leaving that 2 kind of by itself, as you can see. So when we pull this out, you'll notice that this is just a matter of a positive and negative change. However, you'd be thinking again that these aren't so clear cut, and you'd be kind of correct. However, you're also wrong, because again, with the imaginary number, you'd think, hey, that's going to throw us through a loop. No, it's not. And I'm going to erase to make some space here real quick. Because when we evaluate this using kind of like a series-esque kind of use, we get that. Notice that it's cosine k delta x plus I sine k delta x, but when you have that negative exponent, it becomes negative over here. So what does that mean? It means that in the context of adding these two together, that these, the imaginary numbers, cancel out. We don't have to worry about it. So what does that mean for our equation? Well, let's clean it up a bit and let's talk about it. Okay, so what we did here is we basically canceled out the Tnj, rewrote this part, pulled out the 2 to match with the r, and you get this equation. So what's the significance of this equation? This equation helps us kind of understand what's going on, because on this side over here, what this part is saying is that every time you iterate and the heat diffuses, because we start with greater temperatures on both sides of our bars, every time you go forward in time, it's heating up, which means that this value has to be greater than 1, right? Which means that if you go the other way, that heat diffusion has to be kind of like less than 1. So again, I'm going to have to make some room here, and I'm going to finish out this kind of like final thought. So, like we said, if we go backward, it has to be less than 1, correct? And r is what's giving us trouble here. So we don't, this side isn't necessarily what we're looking at. We care about kind of this part. So we find this to be true, that this side has to be less than 1 to keep us from just slingshotting to infinity. Now we can keep doing this all day and eventually go to it, but I'm going to jump straight to the conclusion. Once you get down to the bottom of it, r must be less than 1/2, which means that when we were running our time constants in our code, we had the, alpha was 1, I left it up there, and we were screwing with the time, which means that the delta x, which was also 1, if I remember correctly, we left time as 1/2. So when you mess with that, our r was defaulted at 1/2. Now, it says that r has to be less than 1/2, but when we were observing 1/2, it didn't look too bad. That's correct, but as soon as we started going over 1/2, we started to notice that fluctuation. Now, this part proves that this stability has to be, something has to be done here. Now, when we move into part 5, we're going to help figure out this part and what exactly is wrong with this very crude looking equation over here to help us get into coding again and figure out what exactly is wrong with this crude code. So I'll see you back in just a second. Welcome back. It's time to start part 5. So the Crank-Nicholson equation for basically this equation is similar to ours. However, it allows us to release the constraint of r. So I've taken the liberty to write out originally what we took away from this equation for our very crude equation. And I'm now going to write a little bit cleaner version of Crank-Nicholson's here. So allow me to write this out. As you can see here, there is one noticeable difference, and I know it's a little hard to see, but t to the n plus 1 is in here instead of just when we complete this part is present right here. Although the delta x is factored out, or the delta x squared is factored out over here, this part is basically this top part put together. But as you can see, instead of just having that tj to the n, we have this n plus 1 up here. And what we're doing with this massive chunk over here is we're taking basically the temperature at one point, adding the previous temperature, and taking the average of the two. Because the Crank-Nicholson equation does this, this allows us to get around the constraints of r. So we're going to rewrite this a little bit, and since it just takes up so much room, we're probably going to have to do this in multiple parts. Okay, like I said, this is going to be needed in multiple parts. So to finish up this last section, we're going to skip a lot of algebra manipulation, and we're going to jump straight to this equation right here, which may look familiar. So with some basic algebra manipulation, we can infer a couple things here. The first one is that this cosine k delta x minus 1, that part's always going to be greater than 0. So let's represent that a different way to help explain this restriction. I'm sorry, I think I said that. I'm confusing everything. Why did I say that? I got my words mixed up there. What I meant to say is that this will always be greater than 0. Because this will always be greater than 0, 0 can't cancel out our entire thing here, so we're just going to represent this as the variable y. And we're basically just evaluating this entire part in here, so I'm just going to control this part and ignore this equation part. So this entire part needs to be less than 1. And how we're going to evaluate that? So we know that y is greater than 0 here. So what's the next part we need to evaluate? Well, r is constant on both sides, but we don't necessarily understand what r is, but r has to be relative to 1. Okay, so we may not know what r is, but we will in theory know what y is, and it's a number greater than 0, and we know we have a positive 2 here. So let's represent it as this. So the whole thing comes down to, does this check out? 1 minus z over 1 plus z is less than 1. Is this statement true? And it is 100% true. And this statement is what proves that r has no restriction here. Because within z, it doesn't matter what r or y is, because we already kind of have an idea of what y is, but it doesn't matter what r is. Alright, welcome back. So now that we've gone through and prove that the Crank-Nicholson provides no restriction to our r value, we can go through and solve the matrix required to better help us visualize this change in heat diffusion across our bar. So I've taken the liberty, as you can see up top here, our bar has 50 segments at 1 meter each, so it's 50 meters long. I now have a much greater time value than we had previously to just help demonstrate. It'll give us that better looking curve. Alpha remains 1 for heat diffusivity, and our time value is going to just be kept at 0.5 to keep things simple for us. And then, of course, our R value and our basically distance tracker are all kept the same. So now we should actually take down our bar as well that we had earlier. So when I say bar, what I'm saying here is that TNP full and X20, what this is basically saying is that our bar of 50 segments is all at 20 degrees, and then I correct it with T of 0 is equal to 50. That means that for you, if you were to do this in front of your face, the leftmost value is at 50 degrees Celsius, and then T minus 180, the rightmost side is equal to 80 Celsius. So that's all we've done. And it's basically just the easy setup. So now, as I mentioned, we need to solve that matrix. So how do we want to set up a matrix? Well, we're going to start by setting it with nothing but zeros, so just an empty matrix. Now, this matrix is basically kind of like a 48 by 48-ish. 48 is the most important number, given that the way this matrix is. The matrix has diagonals, so from the top left to the bottom right, there are 3 diagonals that run parallel to each other that we want to extract. So we're just going to kind of go around this by kind of stealing from our temperature value, so to speak. Allow me just to write it out. Okay, so for our first diagonal, we have, I apologize again for me being such a slow typer, but I really don't want to make any errors. For our first diagonal, like I was saying though, it's entirely negative r, and I'll explain it better once we, actually no, let's just put it in right now. So what we're going to be essentially, how do I explain it? Really hard to explain sometimes. Our second value for banded, which we're going to be using to solve, is actually the equation we had earlier. It's going to take me a second to write out though. And it follows the same array values that we used previously, except we are using the new equation. We're using this new equation to more accurately get around that previous problem we had with our r values. Oh my god, typing is such a pain for me sometimes. So that's B. So you'll notice that that's the same format as the equation we solved on the whiteboard. And if I scroll back up here, you'll see that we use the same parts right here. This 2 colon 1 colon minus 1 and then colon minus 2. And those are present down here as well with this kind of added bit in here. So knowing that, this is what this equation is, in part something that feeds back these diagonals. So the first diagonal spits back negative r, which would be the top of the parallel, and if we go down to the next parallel, we would get, making sure it's running, I put the thing there. We get the 1 plus 2 times r part right there. And then of course the third diagonal. This one is also equal to negative r. So to help us with the matrix, we're multiplying by this b value is actually also going to be held in an array. So we need to make this using numpy zeros. And like I said, matching number is 48, so 50 minus 2. Now, this side has the original values are tied to it. So what we need to do is the original value is going to be equal to whatever was calculated in the previous equation plus r times the t value we set up, which this is the left side, so it would be 50. And then, of course, the final value is going to be equal to whatever was calculated plus times the final value, which was our 80. So with this, we're actually largely done. We should have everything we need to use solve banded. And when I say solve banded, actually, it's the Skippy import we had at the very beginning that I said will help us with later, and it's going to help us now. It's going to help us integrate these matrix computations and help us visualize them. So I guess to start off, we'll start off by making our figure. I'm thinking something else. And once again, I'm just slow typing, so I'm sorry. Okay. So now, like we did last time, we need to set up our for loop. And then the first part here is to use solve banded. Then A is our matrix of diagonals that we're going to use, and then B is what we're using to assist us. Then we can actually just take this segment of B values, make sure everything's lined up properly, and now due to like NT's 2000 up here, we're going to need to set up a modular to help us with such a large value, because we don't want to plot every single value. So we'll go with something like 100. That'll reduce it by a significant amount. I forgot. There we go. So again, add the scatter plot so we can round this out and see the change over time. And then I run it and see if there's any errors, I guess. And there is, of course. Okay, welcome back. So, what happened? So, if you remember correctly, we had an error that was focused around this part up here. I didn't spot it for some reason right away, but I cut just to figure out what the error was. I forgot to put an S here, and it just said 0 instead of zeros, even though this one down here had an S. I didn't catch on very quickly, but we fixed it. Another little detail is, instead of using an index of I right here, I multiplied it by delta t, so you can get this nice graph when you run it that shows you over time what it essentially does. And you'll get this visually relatively straight line showing your diffusion of your heat you have your sharp initial down here, and then you have B. This is like the calculated B and whatnot as it goes down here for the initial time frame. And then you have your nice curves going through here. And I mean, that's all for this problem. The appropriate equations and everything you need to visualize the diffusion of heat across your bar. And of course, the conditions of the bar, the 50-meter long bar, heat diffusivity of 1 meter squared per second. It's got 50 sections of 1 meter each. The time skips we used were 0.5 seconds. And then the heating of the bar on your person's left was 50 degrees Celsius, and the heating of the bar on your person's right was 80 degrees Celsius. And that concludes the final part of this problem.